Well, it looks like we can start, and it looks like you're the only one in today. I'm glad you were able to make it. Attendance is beginning a little bit sparse, and I don't think the upcoming holiday is helping at all, but we'll still get through the material for our work today. On the list for the announcements, the third, not exam three, hang on. We're not that far yet. Let me revise that. The exam number one, that's the one we took, is going to begin grading on Friday. I'll try to get that graded as soon as possible, probably getting grading completed sometime on the afternoon at latest. If I don't get it complete on Friday, my goal is to have it done probably first thing Saturday morning, so I don't go too far into the weekend. And aside from that, because of our 4th of July holiday, we won't have class on Monday of this week, just to give everyone an extra bit of a breather. It's a pretty nice holiday that we're about to have, and I think a lot of people are potentially not even going to be in town over that holiday. And so for that reason, we won't have class on Monday. It'll be considered kind of a catch-up week. And yeah, I have had classes before. Usually classes with the lowest attendance is things like Math 1108, Intermediate Algebra. And that one particular class, I had people not showing up for an entire class on multiple days. It was kind of weird, but I got used to it. It's unfortunate because it just means I go faster because there's less questions, and that's not always the best thing in the schedule. But for an online class like this one, definitely for a summer class right before a holiday, I wasn't too surprised for low attendance. We might get a few more to join later on. Well, our work for today is to finish up the section 3.6 notes. We're on the last example, number 3, with multiple parts. And then we're going to start bringing back our work on derivatives a little bit more to grad level, looking at some applications to see some practical uses and to study just what's going on a little bit more with that derivative. It's not just about moving powers around and chain rules and product rules. It has some very massively important applications. The section 3738 and section 3.9 are all going to be important applications. And then chapter 4, its title is Applications of the Derivative. So in a certain sense, we know a lot of our differentiation tools, our properties of derivatives so far. Really what we're doing now is looking into their applications before we go off into chapter 5, the next topic on integration. But any questions at all before we get started today? Okay, let's jump in. Again, hopefully others join in, but if it's just going to be the two of us, we'll still get through it. So we left off on example 3, and the section title was Derivatives of Logarithmic Functions. But there's even more going on here. We're going to revisit derivatives of trigonometric functions, so we can see how to take the derivatives of their inverse functions. So these are the new derivatives, all 6 here, for these notes. The reason the author decided to put these derivatives in this section is because deriving any one of these is essentially just a matter of using implicit differentiation, much like how we showed how to get the derivative of the natural logarithm being 1 over x. So there's now 6 and 6, 12 derivatives altogether. It's kind of like taking a trigonometry class where there's lots of memorization. But like we mentioned back in section 3.3, the derivatives of trigonometric functions are things that come up routinely every single calculus class, any class that uses calculus, physics, engineering, and so on. And it's the same story for the inverse trigonometric functions. There's plenty of times where there's going to be a question that's going to ask you to integrate this in a calculus 1, 2, or even 3 setting, and we just have to know that the antiderivative is tangent inverse x. That's weird because we haven't gotten into antiderivatives, but it just means going backwards from the right to the left. So these are 12 formulas that are massively important to memorize for a calculus setting. While we're learning calculus 1, these would be good ones to include as notes for your exam 2, notes on exam 3, and notes on the final exam. But the more you can memorize these, the better you're going to be able to work with them in a more fluent way. You won't have to look up every single thing once a derivative of secant comes up or a derivative of cotangent inverse comes up. If you know those down pat, then all the next work that comes up is going to be much easier to get through. And we did mention strategies for memorizing these. Borrowing from those strategies, notice that if you dare take the derivative of a cofunction, that's the one and only time, well, it happens 3 times on that table, that a negative sign comes up. So it's nice to see that pattern is revisited here for the derivatives of inverse trigonometric functions. If you take the derivative of inverse cosine, there's a cofunction, so a negative comes up. And same for cotangent inverse and cosecant inverse. So the organization of negative signs is entirely the same. Then beyond that, I would say a next good strategy for memorizing both tables at once is to kind of chunk things together. Our brain likes to see patterns and then likes to see things in chunks. If you're memorizing a phone number, sometimes we want to memorize 3 to 4 digits at a time, for example, to get the whole phone number down. And here's the chunks you'd want to memorize for both of these tables. Put sine and cosine together, sine and cosine inverse together. We have to know just from rote memorization, not the funnest thing in the world, that the derivative of sine is cosine and that the derivative of cosine is negative sine. Then when we look at these two formulas, we can see that there's a nice pattern here. They're almost completely identical. If you have the formula for sine inverse down, it's 1 over the square root 1 minus x squared. Then the one for cosine inverse, it's just off by a sign. It's almost the same exact formula, which is really quite nice. So that's one chunk to bring together. The next chunk is the tangent and the cotangent functions. If you've memorized that the derivative of tangent is secant squared, well, you have the derivative of the one on the right as well. Just change tangent to cotangent. Then the right will have negative cosecant squared. So you go from a function to its cofunction, and you have the next derivative down. Same idea on this table. That's a nice miracle that occurs for these derivatives. These are also completely identical, except that they differ by a sign. The tangent inverse derivative is 1 over 1 plus x squared, and the derivative for cotangent inverse is just negative 1 over 1 plus x squared. So same pattern, just different grouping. And notice how they go. We group sine and cosine, tangent, cotangent, and next we group secant, cosecant. Like before, to memorize this grouping, have this one down pat just by rote memorization. Then you go from a function, secant, to its cofunction, and you have the other formula. Be sure to include the negative sign, but you're expecting it because that's the derivative of a cofunction. Secant goes to cosecant, tangent goes to cotangent, and that's the whole story on that one. Then down below here, the one I would memorize is the one for secant. The derivative of secant inverse is 1 over x times the square root of x squared minus 1. Then for cosecant inverse, same thing, except there's a negative sign. So that's 6 derivatives altogether. The ones on top are from section 3.3, and these are the new ones. Our goal is just to practice working these with a few more derivatives to see how they go. As we progress through the course, this stuff is just going to come up more and more in different kind of settings in chapters 4, 5, and 6. But that's the rundown of these two tables. Any questions with them at the moment? Okay, well, it starts differentiating them to see how they go. It's really just a new set of properties for derivatives, new functions, the inverses here. Here we're asked to differentiate tangent inverse of the natural log x, and we need to be pretty careful with these. Notice it's tangent inverse, then parentheses, natural log x is going on the inside. That means this one in part A is really just a chain rule. But if you change this format just a little bit different, if you said tangent inverse of x times natural log x, it's a product rule. Likewise, down here, this one is a product rule for that reason. The difference of the product rule versus the chain rule is sometimes kind of subtle to see. This one's a product rule because it says sine inverse of x times cotangent x. But if it was written in this way, I'll fix this in just a moment. Written in this way, now it's no longer a product rule, that's an honest chain rule. The way to spot a chain rule is you have a function, but no x, then a function going inside that involves the variable x, much like in this configuration. The way it becomes a product rule is if it looks like this. Both functions, sine inverse and cotangent inverse, have their inputs x, and they're just being multiplied together. So those are really subtle differences that we have to train our eyes to spot to even start some of these problems. But once we see these, here's the organization for chain rule, using the same color coding for every time the chain rule came up. The inner function is going to be natural log x, function going inside tangent inverse, which is now the outer function. The pattern for the chain rule here is to take f prime of x, first differentiate the outer function, tangent inverse. And that's its derivative right here. It's just a new formula. We go 1 over 1 plus. Every time we use the chain rule, we don't put in the x in the formula. Instead, we put in a placeholder. What's going inside is natural log x. And then we're going to chain on a new derivative. It'll be the derivative of that new input, natural log x. So natural log x goes both here and here at the same exact time. And that's good. That was part of what we were doing at the top of these notes. So we get to review here. Let's put just for a quick note, the derivative with respect to x of natural log x is a really nice derivative. That one just becomes 1 over x altogether. So that's the start, just using the chain rule. We take the derivative of natural log x, that just becomes a 1 over x. And this result is now just 1 over 1 plus natural log x squared times, we copied up to this point, but now take the derivative of natural log x, and it's a 1 over x. And that's the whole derivative. It can simplify a little bit by multiplying across the denominators. I'd probably leave it in its factored form and just call this 1 plus natural log x. Let me put in a parenthesis around that first. 1 plus natural log x squared times x. Not a big simplification, just multiplying the fractions together. So that's what the chain rule would look like in this new landscape for these new derivatives. And Caleb says, so for the exam and homework, we don't need to fully simplify. We can keep the roots. So when you mention roots, which part are you mentioning? Are you talking about, say, like the power 2 or otherwise? Or are you referring to this, like, say, the square roots up here and up here in the formulas? The parentheses at the bottom of the fraction. Oh, so you're referring to the 1 plus natural log. Yeah, you can leave it in this form, the factored form, for the purpose of homework and exams. If you went a little bit further, it would have been just 1 over x plus natural log x squared times x. But either version is considered simplified. One might be preferable, more preferable than the other, but that would depend on the context. So yeah, you could leave it in either form for the purpose of homework settings or exam settings. Well, other questions at the moment? Okay, well, let's try out the next one on g of x. because x appears as an input now for sine inverse and as an input for cotangent, this one is now a product rule altogether. But in a certain sense, this one's also really tricky, not just because of the product rule. Here's the first factor, here's the second factor. What's tricky about doing these problems in section 3.6 is we have all these fancy new derivatives that have been supplied to us, but we don't use them on every single part of every single problem. For example, when we go to differentiate cotangent, we're using that derivative. It's not an inverse function whatsoever, unless we say arc cotangent, or put in the inverse function inverse symbol there to say inverse function. So this one is going to be the derivative from section 3.3, and this one for sine inverse is the new derivative. Aside from that trickery, the mixing these different type tables together, the derivative goes just like this. By product rule, we differentiate the first factor, and the derivative of sine inverse is just 1 over 1 plus x squared. Then we multiply it by cotangent x, just copied in. Go plus. Now, on the next term, we copy the first thing and differentiate the other one. So do the opposite, essentially, of what we did on the first term. So this time, copy sine inverse x. Now, multiply it by the derivative of cotangent x. It's an original function, not the inverse. It's a cofunction, so it's going to involve a negative sign. The derivative of tangent is secant squared. So if you differentiate cotangent, you should get cosecant squared instead. In fact, that is the case. So we get negative cosecant squared x altogether. So that's pretty much it to that step. There's not a whole lot more to do. It simplifies just a little bit if you rewrite this as cotangent x divide by 1 plus x squared. So we can bring this together with the fraction, multiply it to the numerator. And this always looks awkward when you have to put in a parenthesis because of that negative sign. So we can just move the negative sign in front and call it negative sine inverse of x times cosecant squared of x. Then at that stage, I don't see any reasonable thing to do further on that. That would be a good simplification, a good stuff to end on here. So that's 2 down. So far, we've used the sine inverse, we've used the cotangent inverse. I think we're going to use one of these two next. The homework is going to give plenty of extra practice as well. So for the next one, let me see if I can show it in one screen. Part C is going to be cosecant inverse of secant x. This one is going to be yet another chain rule altogether. Because there's no cosecant inverse of theta, it's secant theta itself as the input to the cosecant function. So cosecant inverse is outer, and the thing going on the inside, secant inverse, that's the inner function. So we'll try that out next with our cosecant inverse formula up here. Let's bring it down just to help with the visualization, since these are brand new derivatives. Cursor gets a little funny when I'm on the end of the page. There it goes. And, we might as well not try to squash it in here. Let's go to a new page entirely. Okay, so here's our next one to try. Because cosecant inverse came up, we have to use the table copied down below. It's a chain rule, so the process for chain rule is, let's call this, using Leibniz notation, it'll be dy d theta, since the input variable is theta this time. First, we differentiate cosecant inverse. And cosecant inverse as a derivative is really pretty interesting because x occurs in 2 spots. So that means we have to put 2 placeholders for cosecant inverse itself. It'll become negative because it's a cofunction we're differentiating. 1 placeholder here, that's where the x is, then square root. the next placeholder where we see the x squared minus 1. So as a placeholder schematic for this derivative, that is the derivative of cosecant inverse at, say, any input whatsoever. X if it's x. If it's secant theta, we're just going to drop secant theta into those two positions. But because it's a chain rule, we chain on the new derivative. We differentiate the inner function as well. So if your formula for a derivative involves an input variable x in multiple locations, you might have quite a lot of parentheses now. There's 3 placeholders altogether, but in every single one of them, secant theta goes inside. Okay, so that's the start on this one. And we're nearly done. We just need to take the derivative of secant theta and simplify it to finish off this problem. Any questions at all with just the start on it? Okay, there's lots of interesting things that can happen when we go to simplify this one. You might have noticed that if you see a tangent squared comes up, a secant squared, cotangent squared, or a cosecant squared come up, you should think Pythagorean identity might be useful. Same as if you see a sine squared or a cosine squared come up. Caleb says, so for the chain, every x inside the chain is the second function. Yes, absolutely. So we put the second function in that x there, in the cosecant inverse, and that x there. Then just multiply by the derivative of cosecant itself. Yes, absolutely. There can be chains inside chains inside chains. I think we saw an example of that come up in section 3.4. You'd have to write out a problem that maybe goes, say, cosecant inverse of secant of maybe sine theta, something like that. So then you'd be taking the derivative of secant sine theta, and then that's just a new chain rule. And then instead of a theta there, you could put square root theta squared plus 3, and then that's a chain rule going in another level deeper. And so, yeah, this can go as deep as you want, as many steps, it has to be finitely many steps, and then the chain rule can be applied. Other questions so far? Okay, so this one is a longer problem than what we're doing in part C. Sometimes these are called longer chains. I think that's how our author likes to describe them. Again, we took a look into a couple of those using 3 functions in the chain rule notes in section 3.4. Now for this one, all we have to do is differentiate secant theta. We have that this is -1 over, let me just copy to this line, secant theta times square root. Secant squared theta inside the root, we can rewrite as secant squared theta in this format if you prefer. And then next, the derivative of secant theta. This is the one that goes secant theta, it's again, so itself is part of the derivative, and then you multiply it by tangent theta. Once we have that down, we can do a cancellation. Secant and secant cancels off immediately. And there's a slight simplification in that denominator. That simplification, like we were hinting at earlier, comes from the Pythagorean identities. The identity is that tangent squared, theta plus 1, is secant squared theta. That's not exactly what we have here, but we can make a substitution where secant squared theta is, and just plug in tangent squared theta plus 1. Or we can be even more fancy. You can just subtract 1 from both sides of this identity, and now it's a brand new identity. It's tangent squared theta equals secant squared theta minus 1. And that's an entire substitution you can make. The whole thing can just become tangent squared theta. So now it's negative tangent theta divided by the square root of tangent squared theta. And it's tempting to simplify this even further. In fact, it goes just a little bit further, but we have to be cautious. In algebra, when we take the square root of a squared, a for anything, it's not necessarily a. That depends on the sign of a. The true algebraic formula for this is it's the absolute value of a. So this becomes negative tangent theta divided by the absolute value of tangent theta. But we can't cancel that tangent theta with that tangent theta. We're essentially stuck right at that step. But we did it, folks. That's the completion of that derivative down there. We did a little bit more simplifying it just to practice some more with trigonometry. These kinds of things just come up all over the place, loads and loads of times. But any last questions or comments getting through these new derivatives down here? Okay, well, we did it, folks. That's the completion of section 3.6. Let's make sure this saves. Okay, the next section we're getting into is now into, ignore this part where it says we're on example 3, we just finished it. But now we're getting into sections 3.7, sections 3.8, looking into applications of the derivative. Exponential growth and decay is kind of a fun one in a certain sense. This is a lighter topic because this is something that's studied quite a bit towards the end of Pre-Calculus 1, college algebra. And so we're revisiting this, adding a layer of calculus on top of it. But a lot of the stuff we do here might look pretty familiar. However, here, section 3.7, I think for just about everyone, this is going to be mostly new stuff. So this is going to be a tour of interesting problems. In the homework, there's some similar related problems. They're not all exactly the same, but everything we do here is to help you get set up with the homework. So our goal is to solve all problems in this section, 3.7. And there was problem section 3.3, the very last one that we just completely skipped. We mentioned the reason we skipped that is I forgot I put it on this application section 3.7. So here's the problem down below, example 1, that we skipped from before. So we're definitely going to solve it. And it's a nice problem because we're looking into ordinary motion. So we can talk about a position function, a velocity function, and an acceleration function. Those are things we talked about on the very first day of class, as well as in section 2.7. So here's the notes just recopied from section 2.7 as just kind of a refresher. If we say S equals S of t, that's going to be the position of an object moving in one dimension or in a straight line that we're tracking. What we're tracking here is a mass. Here's the mass, this little solid block, that's going to vibrate horizontally on a smooth, level surface. We're going to track its position as it moves left and right as the screen vibrates horizontally in one dimension, just horizontally. And the equation of motion is x of t. This just means the horizontal position x on that horizontal axis at time t is 8 sine t. So when we said smooth level surface, and we gave that function, this is negating friction 100%. We're assuming that there is no friction at all that's going on here. So even though this is kind of a fictional physics kind of situation, it's still an interesting system to analyze. We can go further on this. The more work you do on this, taking differential equations and add dampening forces, so friction becomes a reality. But here we're assuming no frictional forces. So it's a first look at a system like this to see what would happen if this was just impossibly smooth, and the model would be true for short times, but not forever. Eventually friction will take over and the oscillations, the vibrations will dampen down to nothing eventually. But that's our model, assuming perfect smoothness and no friction whatsoever. So x of t is our position function on this one. And one natural question we might have is, What happens if we differentiate it? The derivative is going to represent the velocity. This will be the instantaneous rate of change of the position at any time t. If it's moving to the right, the velocity will tell you how fast in centimeters per second it's moving to the right. If the mass is moving to the left, it'll tell us when we compute the derivative at a time how fast it's moving to the left. It'll include a negative sign to say moving to the left in terms of centimeters per second. So if we use the same units as we have here, the position function is going to be measured in centimeters. Well, that's the wrong color coding. Let me go back. Position function, that's S above, is going to be measured in centimeters. Velocity, well, it's a rate of change in distance over time. So this will be in centimeters per seconds. I'll use SEC for seconds, so it doesn't get mixed up with S, the position function. And then we can just differentiate that again. So this is the next level, acceleration. We write it as A of t. It's the first derivative of velocity. It's how fast velocity is changing, which is the second derivative of the position function. And here it is in Leibniz notation. A is dv dt, or d2s dt2 as a second derivative. So for example, if my mass is moving to the right, we can ask, what is the velocity? And then acceleration will answer the question of how fast is the velocity changing? Is it speeding up or is it slowing down? Is what the acceleration is asking. Is it about to turn around and go from moving to the right to eventually changing over and moving to the left at a certain time? Acceleration is going to answer those kind of questions. So this is our simple model down below, so we can study these three things all at once: position, velocity, and acceleration. Any questions at all, folks, with the setup to this problem? Okay, let's scroll down just a little bit beyond the refresher information from section 2.7. And the first order of business on this is we want to compute a first order derivative, dx dt, evaluated at a time, t is 2 pi over 3 in seconds. So let's work through that derivative to see what we get. This one is less about taking crazy derivatives and just more about looking into the application of it. So it's not a bad derivative, really. We want to compute dx dt, but dx dt is just the velocity. So what we really want to compute is a velocity at time t. You could call it dx dt if you prefer. That's just changing to Leibniz notation. So whatever notation you use, all you're doing is coming back up here and differentiating. So it's going to be 8 sine t prime, which is going to turn into 8 cosine t. So this gives us the velocity at any time whatsoever. We're concerned about the time 2 pi over 3, so we compute velocity at 2 pi over 3. This is the same expression in Leibniz notation, now using just ordinary function notation down here on the left. Either way you visualize it, all you're doing is you're taking 8 cosine at 2 pi over 3. We need to get the exact evaluation for this. So let's put in, just as a reminder, for exams and homework, compute the exact value. In some cases, problems will ask us to approximate, but for this one, we want to know the absolute exact value for the velocity at that time. So here's our big second time doing this. Fast way to do it is just reviewing our trigonometry. In section 3.3, the entire unit circle diagram is provided, but there's several key angles that involve multiples of pi over 3, pi over 6, pi over 2, or pi over 4. If you memorize where these angles are, you have a pi over 3 here, 2 pi over 3 here, or pi over 3, and 5 pi over 3, it makes evaluating these really quite fast. So 2 pi over 3 is right at this position. Because we're computing cosine at that value, it's going to be the x-coordinate. And in this diagram, the x-coordinate is exactly -1/2. So this becomes 8 times -1/2, which gives us -4. The units are in centimeters per second. Let me use a different way to emphasize that. So it's -4 centimeters per second. So that's the evaluation of the derivative. And we've done this before, I believe in section 3.1. A harder thing next is saying what that represents in context of this problem. But that's the first part of the battle there. We have -4 centimeters per second. So that's the velocity. That's how fast it's going. But it's also the direction it's going. -4 means it's moving now to the left. It may not be in that position. That was just one static image. It might be actually right over here is where that mass is. Or maybe even over here. It's just coming back towards the left. And it'll eventually rebound and move towards the right as it oscillates. So our interpretation here for this one would be, to find a spot to scroll to, sorry, just trying to maximize the space here. For the interpretation, this would say at 2 pi over 3 seconds, that was the time we input into the velocity function, the mass is moving to the left at a speed of 4 centimeters per second. Notice I didn't put in the negative there. That would have been double negation. We already said it's moving to there's a negative sign in the derivative the moment we said moving to the left. So that part right here is because the derivative is negative. And we said speed here instead of velocity. Velocity is speed and direction, but we already mentioned the direction. It's going towards the left. So we just said speed instead. Well, that's a problem so far. We have the position function at any time. We just took the time 2 pi over 3 specifically. We know how fast and what direction it's going. But we also might be curious, how fast is the velocity changing at time 2 pi over 3 seconds? Is it speeding up or is it slowing down, in other words? The acceleration is going to answer that. Any questions or comments before we go to another layer in, acceleration next? Okay, let me copy the picture down so we have a visual as we go on to the next stage. So there's our spring and mass system. We computed the velocity. Let me bring that back up and got 8 cosine t. This time we're calculating d2x dt2 evaluated at t equals 2 pi over 3. But all that really is the acceleration at time t. So this is completely synonymous. You can either use function notation. It always indicates the second derivative, and that's just the second derivative in Leibniz notation. So first we'll calculate the acceleration, then we'll go back to the practical interpretation in context of the problem. But it's just the same idea as before. To get the acceleration at time t, all we do with that one is we go back to the velocity, which is 8 cosine t, and we just differentiate that. So acceleration is the derivative of the velocity at time t, which is 8 cosine t prime Constant multiple rule says 8 copies in. The derivative of cosine, recall it's a cofunction, so a negative occurs, will become negative sine t. And that's written better as just ordinary -8 sine t. So there's our acceleration, how fast the velocity is changing at any particular time whatsoever. Let's scroll down just a little bit. That should do it. Now we need to evaluate it at 2 pi over 3. Let's use function notation again and say acceleration at time 2 pi over 3. Note, same time that we did the velocity, we found it was -4 centimeters per second. Acceleration at 2 pi over 3 is going to be -8 sine 2 pi over 3, which is going to be -8 times. This becomes square root 3 divided by 2 for the sine evaluation. Let's turn up to that unit circle diagram just for the visual on that. The sine value is the y-coordinate. And over here on the y-axis, that's where we get the root 3 over 2. So putting that all together, we're finally just about the conclusion of this one. Hard to scroll back to where we were. There we go. This simplifies to -4 root 3. But now the units these are kind of interesting. It's not centimeters per second anymore because it's the rate of change of velocity. This becomes -4 root 3 centimeters per second. So it's how fast velocity in centimeters per second is changing with time. There's the other per second. And that's just a really, really awkward way to write that unit. And so the way we'd usually write this out using unit analysis is to call this -4 root 3 centimeters per second squared. So if we're dealing with acceleration, it's going to be the distance unit in the numerator always, and the time unit squared in the denominator. What it is in its expand form is this, and that's just how we simplify it down in unit analysis. So that's the acceleration of this. The acceleration indicates a leftward direction. And so now that's going to be our hint on the practical interpretation. Any questions so far, folks, on just getting down to that acceleration there? Okay, so what we know so far is that at time 2 pi over 3, our mass, which is right here, it's moving to the left, and the rate is 4 centimeters per second. I didn't put the negative sign on because I indicated the direction to the left with the poorly drawn arrowhead. Let me see if I can improve that. Moving to the left, so the direction is there. And there's the arrowhead. So going in that direction at the rate 4 centimeters per second. But now it says the acceleration is -4 root 3 centimeters per second squared. That means it's speeding up in our interpretation. So we can say here now for our practical interpretation, at 2 pi over 3 seconds, the velocity of the mass is speeding up. And let me put, just for completeness, and moving to the left, which we knew from the prior part. At a rate of 4 root 3 centimeters per second squared. And once again, in the practical interpretation, only reason I dropped the negative sign is because we know the direction already is going to the left, which would mean if it's going to the left faster and faster, it's speeding up. So we said that as well when we wrote that there. So that's our practical interpretation altogether on these kind of things. This probably invokes a lot of interesting questions that we should answer before we finalize this problem. But any questions at the moment? Okay, so the short story of this is at 2 pi over 3 seconds, it's moving to the left at the rate of 4 centimeters per second, but it's also speeding up. What it must have happened is in the oscillation, it must have gone all the way to its rightmost position. Then it's at rest for just one instant in time. Then it started to slowly move to the left, and it sounds like it's accelerating at this time at 4 pi over 3 centimeters per second squared. And the additional thing to keep in mind here is there's a specific reason it's speeding up. So let's put down just a couple pieces of interesting information about this. If v of t, velocity, and a of t, acceleration, have opposite signs, the object is slowing down. So if velocity is positive, but acceleration is negative, that means you're losing speed over time. Or if velocity is negative, like in our problem, but acceleration came out positive, that means it's slowing down as well. It's not moving to the left as fast. Velocity is changing. It's becoming closer and closer to zero. However, if we have a situation like what we have here, if v of t and a of t have the same signs, the object is speeding up. So in other words, if velocity is negative and acceleration is negative, like in this problem, it's speeding up. And that can happen with, say, dropping something from, say, a height of 70,000 feet, say a skydiver. So that's pretty high for skydiving probably, but anything that's going down, velocity is negative because your position is falling with a vertical axis. Acceleration is negative. The acceleration due to gravity pulls you down. And so your velocity is just increasing, you're speeding up. So if you have the same signs, either both negative or both positive for both velocity and acceleration, that's when things speed up. Opposite signs are when things slow down. So we've learned a lot of calculus, and this is just taking another look at the physical situation using tracking things in one dimension in physics for position, velocity, and acceleration. We're going to take a look into other kinds of interesting contexts here for applications. Next one will be population modeling. Then we'll get into a kind of a geometric problem, and then get into something in relativity, which will be kind of interesting. But any questions at all so far with this one? Okay, let's change gears to the next topic. The topics are kind of random here. They're a collection of all sorts of interesting things. And the next random topic is this one. Now we're looking into population modeling. This model is actually a pretty common one. This is referred to as the logistic growth model. In the next section, we're going to look into exponential growth, exponential decay. Exponential decay happens to be very useful, but exponential growth is a very limited use because things cannot grow exponentially forever. That's impossible. Those models are only accurate over short, reasonable timelines. And so if you want a more accurate model aside from exponential growth, that would be the logistic growth model would be a good choice. So here's our growth model. It says the number of yeast cells in a laboratory culture. So this might be some kind of experiment with maybe brewing beer or something along those lines. The number of yeast cells in a laboratory culture increases rapidly. Only at first, it's growing almost exponentially, but it can't do it forever. The growth rate eventually levels off. That's what this model is going to convey. The population is modeled by this function. You could either call it n for number of yeast cells. We're going to use the function notation f of t to model that when we model that function. T is time measured in hours. We have constants, A positive and B positive. So these are constants. And that's a really important observation for us to make, because when we differentiate anything involving a constant, we're either going to use the constant rule, the derivative of a constant is zero, or the constant multiple rule, the derivative will pass through the constant and differentiate the function. So observing that those are constants in the problem is really critical. The only variable here is t. So next bit of information we know is that at time 0, the population is 20 cells. Let's organize and start by writing F, that's a population size. At time 0, 20 yeast cells, cells for short. And it says next, at that time 0, it's also increasing at a rate of 12 cells per hour. The biggest buzzword here of all time is when it said rate. That word is really, really critical to this problem, because at the moment it says rate, speed, velocity, anything along those lines, we're talking about a derivative. So we're always going to make a really big deal out of any time we spot a buzzword like that. Rate is implying the derivative at time 0 is 12 cells per hour. The fact that it comes in as cells per hour, say like meters, centimeters per second in the last problem, also clues us in. We're talking about a derivative now. So if you write down that information, it's saying f prime at 0 is 12 in units of cells per hour. So there's a part B to this one, but let's hide it for the moment while we focus on what's going on in part A. Part A says, find the values of both A and B. And this is a pretty reasonable thing to do. Here, if you're doing any kind of experiment and you're wondering what can happen if you're trying to build the function, but you only have prior knowledge about these cells you're using, you know that you have 20 of them, and maybe the company that provided you these yeast cells told you that they grow at that rate, 12 cells per hour. If you had just those two starting pieces of information, and you were really in the brewing industry, or maybe home brewing, you want to use this function, now you have to find the right values of A and B to use the logistic growth model in the very first place. So this problem is very, very applicable just to ordinary real life, more than it seems. So now that we know the initial values, 20 cells, we have a specification on these particular yeast cells growing at a rate of 12 cells per hour. We're going to build the model. That's what it really is telling us to do when it says find the values of A and B. Fit the right values into the logistic model. Well, it's a good amount of algebra. Problems like these sometimes get a little bit messy, but that's why all along in the course, we've seen problems that kind of got big algebraically, a little bit messy, and this is another one of those. Here we're going to need to use the technique of solving a system of equations, nonlinear. We'll start off by focusing on this equation here. F at 0 is 20 cells. This is f at any time t, so plug 0 inside there, and we would get A over 1 plus b times e to the power negative 0.7 times 0 is 20. So all I've done is plug 0 in for t. That makes this become e to the power of 0, but e to the power of 0 is exactly 1. So now we have an equation, a over 1 plus b is 20. And at this stage, kind of stuck. We can't really solve for A and B and get a definite number yet on that. But we shouldn't expect to. If we're trying to solve for two quantities, we're going to need two equations, and we're only using one so far. So that was the starting initial value, 20 cells. We have one equation to work with in our system of equations. So now we need to go into the derivative next, which means we have to find the derivative to even start this out. So let's begin by computing f prime at t. Maybe before we compute f prime at t, it's kind of an annoying setup. It's a quotient, so you might feel like try the quotient rule, but the quotient rule is more work than's necessary because the numerator is a constant. So what you could do with this is reformat the function. F of t can be re-expressed as a times, now grab the entire denominator, 1 plus b, e to the power of negative 0.7t, multiplied by the power of negative 1, and just by laws of exponents, we can move a denominator up into a numerator, and now it's not a quotient rule. But what we've done is we've exchanged a quotient rule for a chain rule instead. It's not a bad chain rule, so it's worth that exchange. In the chain rule, that's the inner function, and the outer function is y equals t to the power negative 1, but instead of t, we have all of that stuff. So it's another application of chain rule when we go to differentiate this. Working from first principles, we can say the derivative of f at t equals, we're moving left to right, but when we land at that a, because a is constant, the constant multiple rule says nothing happens to it. If it was a plus something, the derivative of a constant rule would say it's 0, but since it's multiplying, it just survives, and we move into the derivative of this function. We must first take the derivative of the outer function. An exponent, negative 1, comes down. The new exponent is 1 less, so now power negative 2. But because it's not just t, this would have been negative t power negative 2 if it was. Because it's not just t, we chain on a derivative of something else. And that derivative we chain on is that entire thing, 1 plus b, e to the power of negative 0.7t. That goes here as well, 1 plus b, e to the power of negative 0.7t. So one more derivative to get through, and we have the f prime at t portion. Once we simplify f prime at t as much as we can use that information. The derivative at 0 is 12 cells per hour, but we needed the derivative to even start using that information there. So that's where it's at so far. Any questions before we finalize this derivative? Okay, we want to make this as simple as feasibly possible because we have to work with it further. So here's the next thing I would do to it. F prime of t equals, we're going to make a fraction out of this. A times negative 1 is better written as just negative a. This power negative 2, it's going to be easier to work with if we now drop it down into the denominator, making it positive. So 1 plus b, e to the power negative 0.7t, power 2. Now we differentiate all of this together. The derivative of the 1 is 0 by the derivative of a constant rule because it's not multiplying. Next, when we're right here, that's the constant multiple rule. B is a constant. It's like the number 5, for example. So it just gets copied down. Derivative passes through, and we differentiate an exponential. That's just another chain rule. The derivative of that exponential is going to be the derivative of the base e, which will be e to a power, multiplied by the derivative of that power. So e is the outer function we do first. The inner function is negative 0.7t. We copy in both of those spots. And now we're about there. So when we differentiate negative 0.7t, That's just a negative 0.7. The negative sign here combines with that negative sign, and we just get 0.7 AB, e to the power of negative 0.7t, divide by 1 plus b, e to the power of negative 0.7t squared. So we're getting there. That's almost to the stage we want to be in. We now have the derivative. It's in its simplified form. I don't see anything we can do further to simplify it. And so now we can finally use this initial condition. So the initial condition here, that the derivative at 0 is 12 cells, will allow us to do the following. Let's just write it down here to show where we're using it. I'll drop the unit for the moment so we can focus on the algebra and the calculus. F prime and 0 just means everywhere you see this 0, you're plugging it in for the variable t. And we've done that once before. When we plugged it into this location, e to negative 0.7 times 0 is still just 0, and e to the power of 0 is a 1. So this simplifies a lot when we plug in 0. It just becomes 0.7 a times b times 1 from that evaluation, divide by 1 plus b times 1 to the power 2. From plugging in 0 here in that next evaluation, then we square it. And this whole thing equals 12. Losing vertical space, so I'm going to use the right arrow to say this implies 0.7 AB over 1 plus b squared is now 12. So when we said the derivative of 0 is 12 cells per hour, it allowed us to plug 12 into those spots. And now we really do have two equations. Equation 1 is this whole thing. A divided by 1 plus b is 20. Equation 2 is this whole thing. 0.7 AB divided by 1 plus b squared is 12. It's certainly nonlinear, but we can solve this one by using the substitution method. Variable b appears in two locations. Probably good to just leave it as is. And this first equation, the variable a is easiest to solve for. Just clear the denominator. And when we do that, we can substitute in the value for a right over here and just plug it in. That will make this equation just involve variable b alone, which means we can get a number on b. Substitute back in and we'll get the number for a once we know b. So that's the plan of attack so far. Clear the denominator and we get a equals 20 times 1 plus b. Substitute that in over here, and now the new equation is that 0.7 times 20, 1 plus b times b. Here's a substitution highlighted here. Divide by 1 plus b squared is 12. So if we can solve that equation, we have the value on b, and then we'll immediately have the value on a by the last substitution there, or b in that spot. So all this is just so we can get the build out for the logistic model in this particular situation for these cells. But we're almost there. Let me copy this down below so we know what we started with. Now it's all just boiling down to equation solving. Any questions whatsoever, folks, getting down to this stage here? Okay, well, here's how this equation solves next. It's really not too bad. We just have to clear the denominator again on this equation. We're solving for b, so we don't want it in the denominator. 0.7 times 20 will give us a 14. Then it's going to be 1 plus b times b. This denominator cross multiplies over, multiplies 12. So it's 12 times 1 plus b squared. And now we're just kind of in an algebra situation. We can take this, distribute 14b into this. So we'll get 14b plus 14b squared. Let's maybe expand 1 plus b squared first and then multiply by 12. Foiling that out gives us 1 plus 2b plus b squared. So equation is now 14b plus 14b squared is, now distribute the 12 through, 12 plus 24b plus 12b squared. So we've converted from a rational equation to now a degree 2 polynomial equation. Our strategy here is to get 0 on one side. Because we have the larger quantity of b squared over here, I'd probably put everything to the left. I think that's the easier route to go. So from 14b squared, subtract over the 12b squared, and we get 2b squared. Next, we're taking 14b, subtracting 24b from both sides, so this becomes a negative 10b. Subtract 12 from both sides. It's now set to 0. This could potentially be a quadratic formula situation, but you would still want to reduce this polynomial before we even worry about those kinds of things. Divide by 2 and it's b squared minus 5b minus 6 equals 0. Then you could use quadratic formula, but this one factors pretty nicely. It becomes b minus 6 times b plus 1. That would expand out as the b squared minus 5b minus 6. We want 0 on the right-hand side because now we can solve for both of these factors. The only way one factor or the other ended up to be a 0 is if b equals 6 or b equals negative 1, which is uncomfortable because we have two possible values, and I didn't take a big enough screenshot as I needed. But recall there was one big assumption on these coefficients for the logistic model. Let's scroll or zoom out just for the moment. The big assumption was both constants a and b are positive. So that means this eliminates b equals 6, positive 6 is the only one we can take. I'll put here for the notes. A reminder that b is positive. And that means half the battle is over. We have the b coefficient. Plug it back here and we'll have the a coefficient. So the calculus hasn't been pretty heavy on this one. It's been mostly algebra by real estate, area of space we've been writing in. But now that we have b is 6, we can say b equals 6 implies a equals 20 times 1 plus 6. Substituting that value in, which means it's 20 times 7 for a 140. So our work is done. B is 6, a equals 140. That's all we really had to do on this thing. Doesn't hurt to go a little bit further and just write down the built-out model. So by all the work above, I think we deserve the fancy therefore symbol, the triangles, the triangular dots rather. The logistic growth model for these bacteria is 140 over 1 plus 6 for b, e to the power of negative 0.7 t. So that's our model to fit the situation as provided. Well, now that we have that, there's a follow-up question. So imagine once again that you are doing this for maybe a beer company, you're dealing with yeast cells, and you're wondering if this is the growth model, how much bacteria yeast cells are you going to end up altogether in the long run? That's what part B is asking for. If this is how the population of the yeast cells change from hour to hour, I forgot the time unit on this. Yes, measured in hours. If this is how the population changes from hour to hour, what happens in the long run as time goes off to infinity? This is another buzzword for this kind of question. When it says in the long run, it doesn't mean plug in t equals 10 billion hours or anything. It means take t going off to infinity. In other words, we're just doing a limit on this. We haven't done those in a while, so this is kind of a nice review problem as well. We're going to take the limit as t goes into infinity. So this will be the population change in the long run. If this limit exists, it'll apply the existence of the horizontal asymptote, and that horizontal asymptote would be the carrying capacity for these particular yeast cells. So we're taking the limit of the model, f of t, so it's the limit as t goes to infinity of the model we just built, 140, divided by 1 plus 6 e to the power of negative 0.7t. This is a reasonable step to take because this is not an exponential model. The population size should not go to infinity. So if we made any mistakes here and the numbers are just weird, and this goes off to infinity, that would tell us our values for A and B are not correct, that we need to just go back to the drawing board and see where we may have made a mistake. So we need to do a limit. We have lots of formulas for evaluating limits, but here's the whole punchline to this one. I'm going to use a different color. For taking the limit as t goes to infinity, the numerator is unaffected, it's a constant, and the denominator, the constant 1, is unaffected. There's a constant multiple rule for limits as well. It's just going to boil down to what happens to e to the power negative 0.7t. To do that limit, we need to know what the graph looks like. So here's the graph of an exponential like y equals e to the t, or even 0.7t. So that's the basic graph that we think about when we're looking into an exponential function, but it's not actually our graph. When we did these kinds of limits in section 2.6, we looked at a lot of these kind of graphs. Logarithms, exponentials, tangent inverse even came up. The graph we really want is this one. If there's a negative here, that causes a reflection. It's a reflection across the vertical axis. So it actually looks like this. This is y equals e to the power of negative 0.7t. It has a horizontal asymptote. That horizontal asymptote is at height y equals 0. But that means when we take the limit of this whole function, that piece right there where the exponential occurs, that will have a limit 0 because that function there has a horizontal asymptote as t goes to infinity of 0 itself. So now the whole thing becomes 140 divided by 1 plus 6 times 0, 0 coming directly from this horizontal asymptote following the color coding. That means it's just 140 divided by 7. And so that means we get a value of 20 cells altogether. Hang on, that's not quite right. I did some really bad arithmetic. 6 times 0 is 0. So that's going to be a 140 divided by 1. There's my second try for 140 cells. I thought 20 seemed kind of odd. That's not a lot of cells. So this culture of yeast cells is probably in like a small test tube or something along those lines. And this is the carrying capacity for those specific cells. Well, we did it, folks. That's the top to bottom analysis on this. We did a lot of things. The application of the derivative portion of this really just came into play the fact that the problem mentioned there was a rate, which meant to solve this whole thing for values a and b, we had to differentiate somewhere and work with that derivative. But from then on, it was really just some algebra review, solving a system of equations, and then reviewing limits on the very last step. Well, we'll take a look into another application before we call it a day, but any questions at the moment? Okay, well, here's our next one to take a look into. This last example was pretty intense. And so that makes this one kind of a refresher after all of that. This one is not so bad. That's something that's maybe a little bit easier to visualize. Imagine a pristine lake. There's nothing going on. The water is as calm as can be. And then someone just throws a rock into it. So that's what's happening here. a stone is dropped into a lake. Whenever you're doing a problem like this one, it's probably a good idea to draw something. So here's my stone. It's been dropped into a lake. It creates a circular ripple. So here's my ripple. I'm going to draw it as a circle with the stone in the center, or as best of a circle as I can draw. So we'll use our imagination on that one. As we know when we imagine this kind of experiment, the ripple flows outward as a literal wave, travels outward at a speed of 60 centimeters per second. So put a line there just to convey that information. This right here, well, it's now a radius of a circle. We can call it r at t because the radius changes with time, and the radius at time t is 60 times t. If it's going at a speed of 60 centimeters per second, then in 1 second, it's 60 centimeters out, 2 seconds, 120 centimeters, and so on. So that's our visualization of the problem. The question tells us, calculate dA dt at time t equals 4 and interpret its meaning. Well, this problem, I feel like if this was an exam question, we'd have to clarify what A is here. Let's write this into the problem just for the emphasis. Let A denote the area of the circular, of the interior of the ripple. So A is the area. We made an edit right after the fact that class started. So let's highlight this in red as a revision. I think that's a important clarification. So here's our area A that we're interested in. But because it's the area of a circle, we can just say right away, area equals pi times radius squared. So we've got all the moving parts of what's going on in this problem, the visualization, the geometric model, area is pi r squared. It wants us to calculate the derivative of area with respect to time at time t equals 4. So first thing we should do is just calculate dA dt. So here's dA dt to get us started. But notice how strange that looks when you say dA dt. Because the formula A, well, as written, it doesn't involve t. It's pi r squared. But that's just our first look at on this. There is another function inside of here. It's actually a chain rule altogether because r is a function of time. So this is really a chain rule. There is an inner function. Let me change my number. The inner function, we usually say 2 for differentiate second. That one is the inner. Is r of t. The outer, we do first, is the, let's write this as y equals x squared function, or just the squaring function for short. So if we say dA dt, and we're really using the chain rule, what it really is going to be is equal to is dA dr. So we'll differentiate this with respect to r. So that means 2 is going to come down, r is going to be to power 1. But then we have to chain on a new derivative. We have to differentiate the inner function with respect to time. That's going to be dr dt. But this is just the analysis for the chain rule in Leibniz notation. We take the derivative of the outer function, multiply it by the derivative of the inner function. So here's outer, and here's inner. So if we take dA dr, now we'll have 2 come down, we'll multiply pi, and r is now to the power 1. I'll keep that in green. That's kind of interesting in a way. The area is pi r squared. When we differentiate the area with respect to the r variable, it goes from 2 dimensions in area to 1 dimension. That's just the circumference, the perimeter around the circle. That's a kind of an interesting fact already. Differentiating seems to have collapsed the dimension of the geometric object we're looking at. Then we multiply it by dr dt. We already know that what dr dt is because it says it travels outward at a speed of 60 centimeters per second. And once speed was mentioned here, that's the derivative. Or if you wrote it as r of t is 60t, then dr dt is just 60 in centimeters per second. So our work is about complete. We just need to evaluate the area at time t equals 4. So dA dt, now evaluated at t equals 4, and this is in time seconds, is going to be dA dr, which is 2 pi r. Now this is r at 4 seconds, but r at 4 seconds is just going to be 60 times 4. So we get times 60 times 4. When we go to plug that in, then we multiply it by dr dt. The derivative is constant. It was already supplied to us, 60 centimeters per second. So we take this, multiply by, it might not hurt before I get too far. The radius here is in centimeters. Let's look at the unit analysis on this one as well. And then we multiply by 60 centimeters per second. So that's the radius. We have the area here altogether. And if we multiply all these values together, I think I'm going to need a calculator for this one. Here's what we get. We have 2 times 60 times 4 times 60 again. So 28,800. This is pi. I'll leave it in the exact form by leaving pi there. Let me put in maybe pi last, 28,800 times pi in units of centimeters times centimeters will give us centimeters squared per second. And it has to be centimeters squared because that's the numerator here. The rate of change of the area with respect to time, which is the per second spot. So we imagine we threw down a rock. There's a ripple that propagates outward. The area in terms of centimeters per second, specifically 4 seconds into this experiment, is increasing at that rate, 28,800 times pi. So it's kind of a strange problem in a certain sense. Any last questions or thoughts at all, folks, getting through this one? Okay, I think this one is kind of satisfying because it's just an immediate application of the derivative. And it kind of increases our intuition of what's happening with areas versus a perimeter, circumference in this case, when we just go to differentiate an area formula like this. You'll notice same kinds of things happen if you differentiate a volume formula to get area and so on. And so this is a nice one to think about intuitively and see how the calculus intersects with the geometry as well. So for the next problem, this one now kind of goes beyond what's actually on the homework. It's mostly just for fun. So we'll give this one a try. And with anything I can't finish up entirely on this one, I don't want to run past time today. That'd probably be kind of rude going right into the 4th of July holiday. Anything I can't finish on this one 100%, I'll complete in the notes so that if you're curious on how this one goes, you can come back to it later on. So again, I don't have anything as nasty as this in the actual homework. This is more just to see how the power of the derivative can work and some other interesting things in physics. So as far as physics goes, one massively important thing is force. Lots of analysis in physics is just analyzing forces. And so it tells us this basic fact from physics. The force, F, acting on a body with mass, m, velocity, v, is defined to be rate of change of momentum. Momentum is mass times velocity. And now when we say rate of change, we mean a derivative. So the moment, once again, this came up, it means derivative. And that's why we have a derivative here in the definition for force. So that's a pretty complicated definition when you think about it. Well, it's not the way we usually think about force. A lot of times we say force is mass times acceleration, but that's only if mass is constant. Mass can change, as weird as that sounds, in different kinds of ways. So if mass is constant, you go to differentiate this, you're just using the constant multiple rule. F will become mass times dv dt. So you pass through m, it's unaffected by constant multiple rule. Then you're differentiating velocity. But the reminder on the very top of the notes was the derivative of velocity with respect to time. That's just acceleration. So that's where the a comes from. And it becomes mass times acceleration. And in a more introductory level physics class, this is more often what we're thinking about. Force is the mass times the acceleration, but it came with a humongous assumption. The humongous assumption was this only works if m is constant. M, the mass of the object that has a velocity, does not have to be constant whatsoever. And so that makes the picture for what force is as an equation a little bit more complicated. So that's the next part of the problem. Any questions with the first portion, just the reminder? Or the refresher, rather, for the derivative there. Okay, so now here's where it gets a little bit more crazy. In the theory of relativity, the mass of a particle varies with its velocity. So velocity is changing with time. That's why we have the dv dt there for the acceleration. And weird things happen when velocities get extreme. It turns out for extreme velocities, say velocities that are approaching a high proportion of the speed of light, the mass of the thing traveling will change. And in the theory of relativity, that's how it changes. We have an m naught in the numerator, which is the mass of the particle at rest. That m naught is now considered to be a constant. So we have the mass of something if it's not moving at all. But now we're imagining it starts to really get moving. It's maybe going 50% the speed of light, which is really, really fast, faster than anything mankind has ever devised whatsoever. But let's just suppose it's going that speed, 50% the speed of light. The mass is now changed. We take the velocity, whatever it is, divide by c squared, take 1 minus v squared over c squared, take its square root, whatever that denominator is, divide it into the initial mass, and that's the new mass of the object traveling very, very fast. Here, c is the speed of light, which means c is also constant. So that's the setup of the problem so far. So the problem says, show that force is actually that formula there. It's your initial mass times the acceleration divided by the 1 minus v squared over c squared to the power 3/2. Force is not the rate of change of mass times velocity. Excuse me, it still is the rate of change of mass times velocity. Better thought. Force is not mass times acceleration, is what I think I was trying to get to. It becomes this. And the faster the thing travels, the more important that equation becomes. We want to track things accurately that are moving very, very fast. If we don't use this when we analyze our forces, our computations are going to be sorely, sorely inaccurate. So that's how the problem starts. Let's do just maybe a little bit more setup on this, just to show you about how it goes if you want to take a look into this problem later on. If you're interested in the physics on this, here's what the next steps will look like. Again, nothing too extreme like this going on the homework. This one was meant mainly for fun if we had extra time. And I felt like looking at this one was better than just going into the next section notes, 3.8. So the way you start this one off is you go back over here. Force is equal to the rate of change, d dt, of mass, which varies with time, times velocity, which also varies with time. And because we now have two honest functions of a variable t, both mass and velocity, this requires product rule. Already, that's a pretty big application to calculus, just in physics, using the theory of relativity for analyzing forces. When we use a product rule on this, here's what it looks like. Force is going to be equal to, I'll differentiate this in the same way we typically did earlier in the notes. I'll differentiate mass first, which means I want to copy velocity and put in dm dt. Recall a comment that we made, I think just last class. When we write down to Leibniz notation, we want to put the derivative portion to the far right when we write that out, just so there's no miscommunication that we're also differentiating velocity. Just the derivative of mass, put the constant function in front. Then we go plus. Now this time we're copying m in. We're differentiating v, so it's going to be dv dt. And that's the derivative we already know. dv dt is just acceleration, so we can replace that with an a. So this becomes v times dm dt plus mass times acceleration. So that's the setup to this stage. And now, once we complete the calculus on this, differentiate dm dt, which means take the derivative of this entire function here with respect to time. We'll be able to put in the right expression here, do some algebra to add up the fractions. And the claim is it just simplifies back down to that thing right there. So this is how you would get started for this kind of problem. I think it's a pretty interesting question, but it's another one of those problems where the calculus is not the worst part. The algebra kind of explodes on us. And so there's a lot of steps to write out. Certainly more steps than I would try to rush through in 7 minutes. That probably wouldn't be a fair use of our time. So this should be a good stopping point for us today. Any last questions or comments whatsoever, folks, on the cracking open of this problem here? Okay, well, if you're curious, I'll post these notes tomorrow morning to show what the derivative of that would look like if you want to come back here, see how it goes. But this is the major concept of how you would get started on this one. Yeah, this one would probably be a bad one for the test. I mean, there's some good things here. Like, for example, bigger takeaway is seeing how the product rule comes down. That's probably the more important part. Another takeaway is using, say, substitutions, that's dmdt, or excuse me, dvdt became acceleration. But aside from that, I'd say a better testing problem might be something like, say, this one. In an exam setting, a 75-minute timed exam, that's more appropriate, something like that. If it's a real exam question, I'll provide the formula here so you don't have to be an encyclopedia, perfect knowledge on every geometry formula that can come up. I'll provide the formula in context. I would say this one is a pretty bad test question as well, just because the algebra explodes. It's a good one for homework, but not so fair for an actual exam setting. And something like this would be fair for both homework and for an exam, where the emphasis is just doing the derivative and also giving an interpretation were the major parts here. So the only one that's kind of the odd one out is this one. This is a bad exam question and not even a great homework question either. This is again just mostly for fun to show how powerful our tools are already. Getting into theory of relativity is a pretty big feat for this kind of stuff. But any other questions or comments at the moment? Okay, well, this will be our stopping point for today. Don't forget that we are going into a holiday, so I hope you all have a safe and exciting holiday on the 4th for the 250th anniversary. That's pretty exciting. Try not to go too crazy. Don't drink too much if you drink. And again, we're going to take Monday off. This is going to be considered kind of a catch-up week for us. I'll still be available. If you have any questions, don't hesitate to reach out. I'll probably be getting caught up myself. I'll start grading the exam ones on Friday. I'm going to return them to you the same way I've been returning your homework sets. I'm just going to go into Canvas, upload your grade at a graded copy, just like how I've been grading your homework as well. So you'll get the feedback on each one of your exams. But have a great weekend, folks. We'll be back to this. We'll work on section 3.8. I'm going to bump the due date to make it more reasonable when we come back on Tuesday. Take care, folks.